We're going to look at the common collector configuration in detail in this video. Now, I've already made a video related to the common collector configuration, but in this video we're going to go into more detail. Anytime you see the common collector configuration, your instinct should tell you the gain of this circuit should be just about 1, but we're going to derive it right now in this video. So first, let's take a look at a typical common collector amplifier. We have a source over here with a particular source impedance R sub S, and we have a load resistor over here of R sub L, and the amplifier lies between the two. What I'm interested in finding in this video is the gain, or the ratio of the voltage across the load to the voltage across the source. I'm going to start off by assuming that the transistor is well biased. We're going to assume that it's in the forward active mode. If you've chosen bad resistors, R1 and R2, for example, you could have the transistor in cutoff, and then none of the derivation that I'm about to do will be accurate. So we're going to assume that the transistor is well designed from the get-go. That's going to allow me to replace the transistor with its equivalent small signal model. A small signal passing through this circuit will still see the same source resistance R sub S, but if the capacitor is large enough, a small signal will go right through it, so I don't need to draw that now. When the small signal reaches this point in the circuit, it's going to see R1 in parallel with R2, so let me write that down here. Now at this point, I want to replace the transistor with a model that describes its behavior reasonably well mathematically. So we have the base, the collector, and the emitter. I'm going to label the current going into the base of the transistor as I sub B. The transistor behaves something like a current source that multiplies the base current by some large number beta and drives it through the collector. We then have a small emitter resistance, little r sub E, and then we reach the emitter. In other words, I've replaced the transistor on the left with this equivalent model that describes its behavior. Since this is a current source, it doesn't really matter what it's connected to up here. Down at the emitter, I'm going to go ahead and draw the resistors R sub E and the load resistor R sub L. Again, my goal here is to find the gain, so I'm interested in knowing the load voltage, V sub L, divided by the source voltage, V sub S. The circuit drawing here is still a little bit too complicated to extract the load voltage directly, so I'm going to take one more simplification step. I'm going to replace everything to the left of these arrows with the Thevenin equivalent source. That will allow me to have just a single Thevenin equivalent voltage and a Thevenin equivalent resistor. We'll have the same base current, I sub B, coming out of that Thevenin equivalent source, and I'm going to leave the rest of the circuit alone. If you don't remember how to find the Thevenin equivalent voltage source, you might want to look at one of my previous videos where I describe how to do that in detail. Here, we basically disconnect everything attached to the Thevenin equivalent source, and we find out what the voltage would be. It's going to be just a voltage divider here if I assume that nothing to the right of this point is attached. For the Thevenin equivalent resistor, I can just look to the left and see that we have R sub S in parallel with R1 in parallel with R2. Now what I'm going to do is apply the Kirchhoff voltage law to this loop. The voltages here should all sum to 0. So first we have a voltage rise of VTH. Then we have a voltage fall using Ohm's law of IB times my Thevenin resistance. Then I have another voltage fall through the resistor R sub E. The current going through it is beta plus 1 times I sub B. And we have the same current going through our load resistors. Those all have to sum to 0. We can now factor out I sub b from these three terms and move all the negative terms to the right of the equation. I'm now going to solve this equation for the base current. I'm now going to apply Ohm's law across the load resistor network here. V equals IR gives us a load voltage of beta plus 1 times IB times the load resistance. Let's now substitute in for our IB. And I'm going to write it over here on the right side. I'm now going to substitute in for my Thevenin equivalent voltage. I'm going to actually write it first here. I'm going to write this source voltage on the left side of the equation so that we'll wind up with a gain. I now just need to rewrite the rest of this expression. And when I rewrite it, I'm going to take the Thevenin equivalent resistance and divide it by beta plus 1, and then get rid of the beta plus 1 in these other two terms. So for the numerator, we're left with just RE in parallel with RL. I now have my Thevenin equivalent resistance divided by beta plus 1, and I have only one more term to write, which leaves us with a complete picture of the gain of this common collector amplifier. Now we know that the gain is ordinarily a number that's very close to 1. Let's look at our expression now and find out why. Well, if our source impedance is small relative to R1 in parallel with R2, or equivalently, if our input impedance to the amplifier is large enough, then this first term should be nearly equal to 1. It's always going to be a number a little bit less than 1, but we can approximate it as a number very close to 1. Likewise for the second term, inside the dotted black lines, the expression is usually a very small number. The reason for that is because if you have a small source impedance R sub S and a large beta for your transistor, then the first term goes away. And then secondly, if the emitter resistance R sub E is a number in the range of 10 to 20 ohms or so, that's usually a small number relative to your load or your emitter resistance R sub E. Therefore, in summary, the second term is typically a number very equal to 1 as well. Of course, that only works if the amplifier is well designed. If you start off with a bad amplifier, then the gain may not be 1. But if you design it well, then a common collector amplifier will typically give you a gain of 1. This expression for the gain is not very easy to remember. So on the next slide, I'm going to show you how to use impedance reflection in order to find this expression for the gain almost by inspection. Let's go ahead and get started. I'm going to give you two options for solving this circuit in a much more simplified way. We're going to start off by using impedance reflection to reflect the base resistance over onto the emitter. After we finish, I'll show you how to do it a different way. I'm now going to draw a small signal equivalent circuit, but I'm not going to replace the transistor with a complicated model in this case. We're just going to use impedance reflection. A small signal will see the same source impedance, R sub S, and then it will see R1 in parallel with R2. We now reach the base of the transistor, but I'm not going to use impedance reflection to move the emitter resistance over onto the base. I'm going to do the opposite. I'm going to reflect from the base into the emitter, so we're going to stop right here for the input side. Let's call this V sub 1. It's not the true base voltage, but it's going to give us a correct expression for the gain. We're going to treat the transistor as a voltage source with a gain of 1 because it's common collector. 1 is multiplied times V1. We're now going to have a voltage divider set up between the emitter resistance R sub E and any impedance reflected from the base into the emitter. Let's do the impedance reflection first. In order to reflect base resistance into the emitter, I need to divide by beta plus 1. If I look back from the base, I see three resistors, R1 in parallel with R2, in parallel with R sub S. and we'll divide that by beta plus 1 to properly reflect it over into my emitter. We now have the emitter resistance R sub E and a voltage divider with RE in parallel with RL. This is the load voltage, V sub L. From this drawing, I can get an expression for the voltage gain by inspection. We first have a voltage divider at the input side. We then have a gain of 1 coming from the source, and then we have a voltage divider at the output side. You'll find that this expression is exactly the expression that we just derived using the more complicated transistor model. This one was a lot easier. Let's move now on to option 2, and we're going to instead reflect the emitter resistance over into the base instead. You should only use impedance reflection once to avoid double counting things. So here we're going to go the other way. In this case, we still have our voltage source V sub S, our source resistance R sub S. We now have R1 in parallel with R2, but we have another branch that goes into the base of a transistor. Looking down into the emitter of the transistor, we have emitter resistance R sub E, and then RE in parallel with RL. And everything has to be multiplied by beta plus 1. I'll label this voltage V sub B because in this case it is a true representation of the base voltage. For this reason, I like option 2 just a little bit better. We'll again treat the transistor as a voltage amplifier with a gain of 1 since it's common collector configuration. It's going to multiply it times the base voltage here, V sub B. We then have a voltage divider set up between R sub E and the load resistors. We can again use this circuit to determine an expression for our gain by inspection. For our input side, we have a voltage divider. We then have our gain of 1, and then at the output side, we have another voltage divider. In both of these expressions, I've used green to show where we used impedance reflection. In option 1, we reflected the base impedance over into the emitter. It wound up here in the denominator. In option 2, we reflected the emitter resistance over into the base, so it wound up here in 2 places on the input side. It's not immediately obvious that these 2 expressions are the same, but they are. It's just not so easy to tell that they're the same. In fact, I didn't even want to do it, but I want to prove to you that these expressions are the same. So I coded them into Mathematica. Here's option 1, and here's option 2, and then at the end of the day, the 2 gains are equal to one another according to a computer algebra software. I'm sure if you had enough time to spend, you could find the same thing on your own using longhand algebra. I now want to find expressions for both the input impedance and the output impedance of the common collector amplifier. Let's start with the input impedance. Of course, to find a proper expression for the input impedance, it's not merely going to be R1 in parallel with R2. We also have some current going into the base, so we're going to have to use impedance reflection in order to find out what the resistance is looking into the base. Nonetheless, it's relatively easy to get a complete expression for R sub N. Because at the emitter, we just have little r sub E plus RE in parallel with R sub L, and that's the resistance that I would see if I look from the base to the emitter. Now for the output impedance. To get a proper expression for R sub out, we're going to have one branch going downwards through R sub E, and that's going to be in parallel with another branch that goes up through the emitter. We're going to have to then use impedance reflection to find out what that is. Now, the little R sub E lies to the right of the baseline, so we're not going to want to alter the expression for just R sub E. It's these 3 resistors to the left that are going to have to be divided by beta plus 1. You see how easy it was to find expressions for the input and output impedance once you know how to use impedance reflection. Now look at the expressions and see what we can learn. First of all, the input impedance here is high. It's high because beta is a large number, and if you design the amplifier properly, you can use bigger resistors for R1 and R2. Secondly, the output impedance is small. It's small because beta is a big number and you're dividing something by it, and little r sub e is typically a number on the order of a few ohms. Let's now do some examples and find the real values for the gains of some circuits. Let's find the input impedance, the output impedance, and the overall voltage gain. First of all, I know for the overall voltage gain that if it's a properly designed amplifier, the gain should be a number very nearly equal to 1. Let's see if that's the case. For the input impedance, we have an 8 kilo ohm resistor in parallel with a 10 kilo ohm resistor, and that's in parallel with the resistance going through the base. Using impedance reflection, it's going to be beta plus 1 times the little r sub e, which is in series with a 1 kilo ohm resistor and a 500 ohm load. In order to find out what little r sub e is, we're going to have to determine the DC characteristics of this amplifier. It's a good idea to do that anyway, just to make sure that it's in the forward active mode. The base voltage is going to be roughly the power supply voltage times this voltage divider set up by the 8 and 10 kilo ohm resistors. That winds up being about 5.56 volts. Of course, in reality, it's going to be slightly lower than that because we do have some base current that's going to draw it down, but we're not going to worry about it here. Since the base emitter junction is basically a forward bias diode, the emitter voltage is going to be about 0.7 volts below base voltage. That gives us 4.86 volts here. The DC current is all going to be passing through the 1 kilo ohm resistor. None of it's going to go through the load, right? Because we have a capacitor there blocking it. Using Ohm's law, we then determine quite simply that the emitter current is going to be 4.86 milliamps. Since the collector is at 10 volts, I can immediately confirm that the transistor is in the forward active region. That's certainly good news. We know the emitter current now as well, so I can find little r sub e. It's just going to be 26 divided by 4.86. Roughly 5 ohms, a pretty small value just like we expect. If we assume a beta of 100, an r sub e of 5.4, then we have everything we need to find our input impedance. The base branch gives us about 34 kilo ohms and an input impedance of 3.9 kilo ohms. Just to make a side note here, if you don't use impedance reflection and you want a rough estimate of the input impedance, you can just do 8 kilo ohms in parallel with 10 kilo ohms, giving you 4.4 kilo ohms, which is also reasonably accurate here. Let's now find the output impedance. Now looking back from the output side, we have two branches. We have a 1 kilo ohm branch in parallel with another branch going up through the transistor. Going up through the transistor, we have the emitter resistance R sub E, and then everything on the base side will have to use impedance reflection in order to bring it over to the emitter. We can use it for both the input impedance and the output impedance, but we can't use impedance reflection to find the gain in both places. We can use it for either the input impedance or the output impedance if we're only looking at one of those at a time. Looking back from the base here, we have 3 resistors, 10 kilo ohms, 100 ohms, and 8 kilo ohms. We can substitute in for R sub E, and if we use a beta of 100, we end up with 2 small numbers here on the right side of this expression. 6.3 ohms is a really small number for the output impedance, and that's really what makes the common collector configuration such a good amplifier. We have a nice high input impedance, a small output impedance. The gain, however, is going to be a number very nearly equal to 1. Let's find an overall expression for the gain. The gain is going to have 3 sections, an input section, a gain section and an output section. Our input section is just a voltage divider. The gain of a common collector amplifier is 1. And then on the output side, I'm not going to use impedance reflection here. I'm going to assume a simple voltage divider set up by our load resistor and R sub E, and I'm not going to reflect anything from the base into the emitter. I'm going to stop right at the baseline. The reason for that is because I intend to use impedance reflection on the input side. You should only use it once to avoid double counting things. In other words, we're going to use 3.9 kiloohms here. If you want to use 4.4 kiloohms here instead, then you should, strictly speaking, be using impedance reflection on the output side. If you plug in all these numbers, you get 0.96. So after all of that, we wound up with a gain that's very nearly equal to 1. And that's really true most of the time with common collector amplifiers. Let's work another example where we do the same thing. Let's find the input impedance, the output impedance, and the overall voltage gain. Let's start this time with the DC characteristics. Our base voltage, VB, is going to be some number between our power supply voltage of 10 volts and ground, and it's going to be just a voltage divider. Since these are both 100 kiloohm resistors, I can write 5 volts by inspection. Since this is a forward bias diode, I can go ahead and write my emitter voltage since it's just 0.7 volts below my base voltage. We now have enough information to find my emitter current because that's 10 kiloohm resistor down there. And we find that it's 0.43 milliamps. Since we know the emitter current, we now have enough information to find the emitter resistance, little r sub e, which we can approximate by taking 26 divided by I sub e expressed in milliamps. That emitter resistance here works out to be 60 ohms. It's a bit higher than it was in the last example because the emitter resistance here is larger. It's 10 kiloohms here, and in the last example it was only 1 kiloohm. Let's find the input impedance R sub N now by inspection. So we're going to have 100 kiloohms in parallel with 100 kiloohms in parallel with some resistance looking into the base. We'll have to use impedance reflection in order to find it. We therefore have the two 100 kiloohm branches, and then for the impedance reflected branch, we're going to have emitter resistance R sub E, which is in series with two other resistors, 10 kiloohms and 1 kiloohm, which are in parallel with one another, and all that's going to be multiplied times beta plus 1 since it's reflected. Plugging in an approximation of 100 for beta, this all works out to be about 98 kiloohms. The net input impedance is then 33 kiloohms. When we compare it to our R sub S, which is 10 kiloohms, this is only fair. It's not really a very high number, is it? That means that our gain is going to be reduced below 1, a bit more than it was in the last problem. Let's now find an expression for our output impedance. Our output impedance has two branches. We have one branch looking down the 10 kiloohm resistor and another branch that goes up here through the emitter, and then we'll have to use impedance reflection in order to find out what these three resistors contribute. So we start off with the 10 kiloohm branch, and that's in parallel with the emitter resistance in series with three resistors that I have to impedance reflect. Two 100 kiloohm resistors and a source resistance of 10 kiloohms. This term works out to be about 83 ohms. So when we compare it to our little R sub E of 60 ohms, impedance reflection kind of had to be used here, otherwise we wouldn't have gotten the correct answer. The net output impedance works out to be 141 ohms. That's pretty small, so that's really good news for this amplifier. Let's go ahead and find an expression for the overall voltage gain. Our expression for the voltage gain is going to have three sections here. We first have a voltage divider at the input side. We then have a gain section, which is just one since it's a common collector amplifier. and then an output section. In this case, I'm going to be using impedance reflection for the input side, so I'm not going to use it at the output side. For the output side, we're going to have just a simple voltage divider. If I had used impedance reflection, I would have to have another term to add to the emitter resistance, wouldn't I? But I'm not going to do that here. Let's go ahead and substitute in some numbers. 33 kiloohms for the input impedance, which is correct through impedance reflection. The source impedance here is 10 kiloohms. And then finally, I'm going to plug in 60 ohms for little r sub e. This number works out to be 0.77, and this number at the output side works out to be 0.94. What we can conclude here is that the input impedance here is not quite good enough to give us a gain of 1. On the output side, we're pretty much okay. The net voltage gain for this amplifier works out to be 0.72, still respectable, but not as good as it was in the last case for a common collector amplifier. That wraps it up here for the common collector configuration. In the next video, we're going to do the same thing with the common emitter configuration so that you can get some experience finding good and complete expressions for the voltage gain.